Welcome back, everyone, to The Deep Dive. This time, we're taking a deep dive into the world of transmission media. You know, that stuff that makes our connected world possible. All those invisible pathways that carry our data.
From a simple text message to, streaming a live concert, it's pretty amazing how many ways we figured out to get those ones and ohs from here to there.
You're telling me we've got research articles, deep dives, even some historical anecdotes for this one. And trust me, you'll be surprised by how much of this you use every single day without even realizing it. So let's get started with the basics. What exactly is transmission media?
Well, it's basically the physical medium through which data travels, like the bridge between devices that lets them, share information.
So it's not just some kind of abstract digital concept.
Not at all.
There's actual stuff involved.
Oh, yeah, absolutely. And that stuff can be anything from the copper wires in your walls to the radio waves carrying your favorite radio station or even pulses of light going through fiber optic cables.
So when I'm binge watching my favorite show, my data is literally surfing on beams of light.
You got it.
That's pretty wild.
That's just one example. The diversity of transmission media is pretty astounding.
Now, I've heard the terms guided and unguided media. Is that basically how we categorize all these different types?
That's exactly it. Guided media, as the name suggests, means the signal is confined to a specific path. So you've got your copper wires, coaxial cables, and fiber optic strands. All those physically guide the data along a set route.
So if guided media is like a highway with lanes, then unguided media would be like taking to the open skies.
Perfect analogy. Unguided media uses electromagnetic waves to transmit data through the air. Radio waves, microwaves, satellite signals, and even infrared. No physical connection required.
Okay, so now I'm picturing like data packets soaring through the air like little digital birds. Let's rewind the clock a bit. How did we even get to this point? Where did it all begin?
You might be surprised to learn that the earliest forms of data transmission were very, how should I put it, grounded. Think of those old telegraph lines stretching across continents, relying on pulses of electricity to carry messages in Morse code.
Oh yeah, like those old Western movies, click, 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 with the telegraph operator.
Precisely. For its time, it was revolutionary. Connecting people across continents practically in real time. But those copper wires, they have limitations. Signal strength drops off pretty quickly over long distances, makes them impractical for, high-speed data.
So what was the next step then in this evolution of data highways?
Yeah.
Coaxial cable.
You got it. Coaxial cables were a big step up. Basically, you have a copper wire surrounded by insulation and then a braided shield. That really helped to improve signal quality and bandwidth, meaning more data could be transmitted at higher speeds. They became, the backbone of cable TV networks for decades, really.
So it's all about fighting signal loss and interference. Did coaxial cables solve all the problems, though?
Well, they were a huge step forward, but they still relied on electrical signals. And then came fiber optics, which were, a real game changer.
Okay.
Instead of electricity, these cables use pulses of light to carry data. We're talking mind-blowing speeds here. Terabits per second, enough to download like an entire HD movie in a snap.
Hold on. Light? Like the stuff coming from my lamp. How can that carry data?
Well, it's based on some pretty cool physics. Picture a thin strand of glass, carefully designed to guide light, along its length with very little loss, almost like a perfect reflective tunnel for light, letting those data-carrying pulses travel really long distances super fast.
That's incredible. So my internet is literally powered by light.
Yeah.
Like something out of Star Trek.
It is.
But fiber optics can't be everywhere, can they?
That's true.
That's where wireless communication comes in, right?
Exactly.
Right.
But wireless communication has really freed us from those physical tethers.
Yeah.
But to really understand it, we need to talk about the electromagnetic spectrum. It's a huge range of frequencies. From those low-frequency radio waves used for broadcasting to the high-frequency gamma rays used in, medical imaging.
Okay, now that sounds pretty complex. Where does our everyday wireless communication fit into all of that?
Well, we mainly use a small slice of the spectrum for things like radio, cell networks, Wi-Fi, satellite communication. Different frequencies have different properties, so they're suited for specific tasks.
So it's like a giant radio dial with each frequency band playing a different tune.
Yeah, kinda.
What about radio waves, though? How do they actually travel through the air?
Radio waves are a type of electromagnetic radiation, basically energy moving through space. They can travel through the atmosphere, even diffract around obstacles. And fun fact, they can even reflect off the ionosphere, a layer of charged particles up in the atmosphere. That allows for long-distance radio communication.
Wait, so my favorite AM radio station is bouncing its signal off the sky.
You got it.
That's wild. But, wireless communication isn't perfect. What are some of the challenges with wireless?
Well, wireless signals are prone to attenuation. They weaken over distance, especially at higher frequencies. It's kind of like shouting to someone across a field.
Right.
The further the sound travels, the harder it is to hear.
Yeah. Okay. So signal strength fades with distance.
Yeah.
But I also know that wireless can be unreliable. Think dropped calls, buffering videos. What causes those disruptions?
That's usually interference. Like when your microwave messes with your Wi-Fi, interference can be from other wireless devices using the same frequency or even just physical objects blocking the signal path.
Oh, so it's like a crowded room where everyone's trying to talk at the same time and it's hard to hear anything clearly?
Exactly.
So whether we're talking about guided or unguided media, are there like key features that differentiate them?
Oh, absolutely. Bandwidth is a big one. Think of it as the capacity of the data highway. More bandwidth means you can transmit more data per second, faster downloads, smoother streaming, and less lag.
So it's like a multi-lane highway versus a single-lane road. More lanes, more cars can travel at the same time.
Yeah, that's it.
What about signal attenuation? I know we touched on that with wireless, but does it apply to guided media as well?
It does, definitely. All transmission media experience signal attenuation, even those fiber optic cables. The longer the signal travels, the weaker it gets. To fight that, engineers use repeaters and amplifiers to boost the signal and extend the reach of the network.
Like rest stops along the highway to keep those long-haul truckers going.
Exactly.
And of course, we can't forget about interference. What are some common sources of interference, especially in those guided systems?
For guided media, think about unwanted signals coming in from the outside world. Electromagnetic interference from things like power lines. Or electrical equipment can disrupt the signal traveling through those copper wires or coaxial cables.
Like that annoying buzz you sometimes get on a phone call when someone's using a hairdryer or something nearby.
And with unguided media, the airwaves themselves can get crowded, leading to interference between different wireless signals competing for space in the same frequency band. You can also have those physical obstacles that can block or weaken the wireless signals, leading to those dropped connections.
So it's a constant battle to keep those data packets flowing smoothly and securely. Finally, let's talk about the cost and complexity. I imagine there's a wide range, depending on the type of media.
Absolutely. Choosing the right transmission media is a balancing act. Performance versus cost and practicality. Like installing and maintaining fiber optic cables, it's pretty specialized and expensive, especially compared to running simple copper wires. But the payoff in terms of speed and capacity can be huge.
It's like choosing between a high-performance sports car and a reliable but slower family sedan. Both have their pros and cons, depending on what you need and your budget.
That's right.
Now let's zoom in on a topic close to everyone's heart. Wireless LANs. The world of Wi-Fi.
Wi-Fi. The unsung hero of our always connected lives. It's based on the 802.11 standard. It's evolved dramatically over the years, bringing us faster speeds, greater range, and the ability to connect tons of devices at the same time.
Can you break down how Wi-Fi actually works? I know it involves radio waves, but I'm curious about the behind-the-scenes magic.
Well, imagine a room full of people all trying to talk at once. It would be chaos.
Yeah.
To prevent that, in the wireless world, Wi-Fi does something called carrier sense, multiple access with collision avoidance.
Okay, that sounds a little technical.
Yeah.
Break it down for us.
Basically, it's a set of rules that make sure devices share the airwaves politely. Before transmitting data, a device listens to see if the channel is busy. If it's clear, the device sends a short request to send signal, like raising your hand in class before speaking. If no one objects, the device gets a window to transmit its data.
So it's like a digital version of speak only when spoken to. That's a good way to put it.
That's pretty neat. But I've also heard about different Wi-Fi standards, like 802.1b, 802.11g, and now we have Wi-Fi 6.
Right.
What's the difference between all these versions?
Those different standards represent the evolution of Wi-Fi tech.
Mm-hmm.
Each one offers improvements in speed, range, efficiency. Think of it like upgrading your phone. to get the latest features and better performance. We've seen huge increases in data rates with each new standard, driven by our, ever-growing demand for bandwidth-hungry stuff like streaming and gaming.
It's like a never-ending race to keep up with our data appetite.
It is.
Speaking of pushing the limits, is there any connection between Wi-Fi and those wired Ethernet networks we use in our homes and offices? They seem like completely separate worlds.
You might be surprised to learn that there's a fascinating historical link.
Really?
Early Ethernet, the, wired networking standard that's everywhere now, actually borrowed some key ideas from a wireless network developed way back in the 70s.
Oh, wow.
Called Aloha.
Aloha? What's that? Yeah, Aloha was developed at the University of Hawaii to connect computers across the islands using radio waves. They faced a similar challenge, multiple devices sharing the same channel, leading to collisions and data loss. So they came up with this revolutionary collision detection and retransmission scheme that really influenced how Ethernet handles collisions.
So our wired internet connections actually have roots in a tropical island wireless network.
That's right.
That's an amazing piece of tech history.
Right.
But we can't forget about a crucial aspect of any data transmission security.
Right.
With all this information flying around, how do we keep it safe, especially in the wireless world where, signals are more vulnerable to eavesdropping?
Security is absolutely key, especially when data is transmitted wirelessly. Think about it like sending a valuable package in the mail.
Right.
You want to make sure it's protected. That's where encryption and authentication come in.
Okay, break those down for us. What do they mean in terms of data security?
Encryption is like putting your data into a secret code that only the intended recipient can decipher. It scrambles the information, so anyone without the decryption key can't read it.
So like sending a message in a locked box.
Exactly.
That only the recipient has the key to open.
Precisely.
Got it.
And authentication is like a digital ID card.
Okay.
It verifies the identity of the sender and the receiver to make sure you're communicating with the right person.
So it's like showing your ID before entering a secure building.
Yeah, that's a good way to put it.
It makes sure that only authorized people have access. Makes sense. But what about those public Wi-Fi networks that we find everywhere these days?
Yeah.
Coffee shops, airports, even parks. They're convenient.
They are.
But are they safe?
Well, they can be risky. Because public Wi-Fi networks are often unsecured, meaning your data is transmitted in plain text for anyone with the right tools to see. Imagine sending a postcard with your credit card details written on it. Anyone handling that card could potentially see your information.
Yikes. So someone at the next table in a coffee shop could potentially see my passwords, credit card numbers, if I'm not careful.
It's possible. That's why you need to be extra cautious when using public Wi-Fi. Try to avoid accessing sensitive information like online banking or shopping while you're on an unsecured network.
That's good advice. But sometimes, you need to check your bank balance or make a quick purchase while on the go. Is there any way to make public Wi-Fi safer?
There is. A VPN, or virtual private network, creates an encrypted tunnel between your device and the internet, protecting your data even on an unsecured Wi-Fi network. It's like traveling through a secret tunnel. No one outside can see what you're doing or where you're going.
Okay, so a VPN is like a digital invisibility cloak.
Pretty much.
For my data when I'm on public Wi-Fi.
Exactly.
That sounds like a must-have for anyone who uses public Wi-Fi regularly. I think we've covered a lot of ground in this first part of our deep dive into the world of transmission media.
We have.
From those early telegraph lines to the mind-boggling speeds of fiber optics and the wireless wonders of Wi-Fi, it's been quite a journey.
It has. And we've only just begun to scratch the surface.
We'll be right back to delve even deeper into this fascinating world.
Stay tuned.
See you in a bit.
See ya.
Welcome back to our deep dive into transmission media.
It's amazing how all this technology just works behind the scenes to keep us all connected.
Yeah, it truly is a marvel of engineering and innovation.
Okay, so we've talked about the big picture, guided and unguided media, a bit of history, and the basics of Wi-Fi.
Uh-huh.
Now, I kind of want to get into some of the specifics. You mentioned bandwidth earlier. Can you unpack that a little bit more?
Sure. Bandwidth is essentially the highway capacity for data. It's how much data can be transmitted over a connection in a given time, usually measured in bits per second, or for, higher speeds, gigabits per second.
So the higher the bandwidth, the faster the data can travel.
Yeah.
Exactly. Higher bandwidth means more data can flow through at the same time. Faster downloads, smoother streaming, less lag when you're gaming.
So it's like having a wider pipe to carry more water.
Yeah, that's a great analogy. A narrow pipe restricts the flow. A wider pipe lets more volume through. Same idea with bandwidth.
Okay, that makes sense. Now, we touched on signal attenuation, the weakening of a signal over distance. But how does that actually work? And what are the implications?
Think of it like a ripple in a pond. As the ripple expands, it loses energy, eventually fades away.
Right.
Same with the signal. As it travels through a medium, whether it's a copper wire or fiber optic cable or even the airwaves, it loses strength.
So the further the signal has to travel, the weaker it gets.
Precisely. And that attenuation can lead to all sorts of problems, reduced data rates, even complete signal loss.
So how do engineers fight that signal fading? Is there a way to kind of boost the signal as it travels?
Yeah, that's where repeaters and amplifiers come in. Repeaters are like signal relay stations. They receive a weak signal, clean it up, and retransmit it with renewed strength.
So it's like relay runners, passing a baton to maintain speed over a long distance.
Exactly. Amplifiers, on the other hand, just boost the signal strength without actually interpreting the data, like turning up the volume on a speaker.
Okay, so repeaters regenerate the signal.
Right.
And amplifiers just boost the volume.
That's right.
Now let's talk about interference, the bane of clear communication. What are some common culprits, especially in the wireless world?
Interference is anything that disrupts or distorts the signal. In the wireless world, think of it as a crowded radio frequency spectrum where lots of signals are all competing for space.
Right.
You might have interference from, other wireless devices using the same frequency, like a Bluetooth device messing with your Wi-Fi.
Oh, so it's like trying to have a conversation at a noisy party where everyone's talking over each other.
Yeah, exactly. And just like at a party, physical obstacles can also create interference. Walls, trees, mountains, they can all block or weaken signals.
So it's not just about distance then, it's also about, the environment that the signal travels through.
Right, exactly.
Now we've talked about bandwidth, attenuation, and interference.
Yeah.
Let's shift our focus to security, especially in the wireless world, where signals are more vulnerable to eavesdropping. What are some key techniques to keep our data safe?
Encryption is really important. It's like putting your data in a secret code that only the recipient can decipher. Encryption algorithms scramble the information so anyone without the key can't read it.
So like sending a message in a locked box that only the recipient has the key to open.
Exactly. Another crucial security measure is authentication, which verifies the identity of the sender and the receiver. Think of it like a digital passport confirming your legitimacy.
So like showing your ID before entering a secure building.
Yeah, good analogy. It ensures that only authorized parties can access the network or certain resources.
Right, okay. That makes sense. Now let's talk about public Wi-Fi networks. We found them everywhere these days. Coffee shops, airports, even parks. They're convenient but also seem kind of inherently risky. How do we stay safe when we're using public Wi-Fi?
Public Wi-Fi can be a security nightmare because it's often unsecured, meaning your data is transmitted in plain text, visible to anyone with the right tools. It's like sending a postcard with your personal info written on it. Anyone handling the card could read it.
So someone sitting at the next table in a coffee shop could see my passwords, credit card numbers, if I'm not careful.
Yeah, it's possible. That's why you've got to be extra careful on public Wi-Fi. Avoid accessing sensitive stuff like online banking or shopping if you're on an unsecured network.
Good advice. But let's be realistic. Sometimes you need to check your bank balance, make a quick purchase on the go. Is there any way to make public Wi-Fi safer?
Absolutely. A VPN or virtual private network creates an encrypted tunnel between your device and the internet, shielding your data even on unsecured Wi-Fi. Imagine you're traveling through a secure tunnel. No one outside can see what you're doing.
Okay, so a VPN is like a digital shield for my data when I'm on public Wi-Fi.
That's a good way to put it.
Sounds like a must-have for anyone who uses public Wi-Fi a lot. Now let's dive into the different types of guided media. We briefly mentioned coaxial cables and fiber optics earlier, but can you go into a bit more detail about their pros and cons?
Sure. Coaxial cables with their insulated central conductor and braided shield were a big step up from traditional wiring. They offer better bandwidth, less susceptible to interference. Think of them as the middle ground between basic copper wires and the high-speed world of fiber optics.
So they were the kind of go-to for, cable TV and early internet connections.
Exactly. They're still used in some cases, But fiber optics have largely taken over for high-speed stuff. Fiber optics, those are like the super highways of the data world. They transmit data using pulses of light, which travel crazy fast with very little signal loss.
It's amazing to think that these thin strands of glass can carry so much information so quickly. But I imagine installing fiber optic cables must be a complex and expensive process.
It can be. It requires specialized equipment and know-how. But the long-term benefits, higher bandwidth, lower maintenance costs, greater longevity, often outweigh the upfront investment.
So it's like investing in a high-quality appliance that will last for years instead of a cheaper model that might break down sooner.
Yeah, good analogy.
Now, we talked about coaxial and fiber optics, the modern marvels. But let's not forget about those early telegraph lines that started it all. They seem almost ancient in comparison.
They were a remarkable innovation for their time. Think about it. Sending messages across huge distances using electrical pulses traveling through copper wires.
It's hard to believe that was cutting-edge technology, not that long ago. How did those early telegraph systems even work?
The basic idea was to send electrical pulses of different lengths through a wire. At the receiving end, these pulses were interpreted as dots and dashes, which formed the Morse code alphabet.
Like those scenes in old Western movies where the operator's tapping out messages.
Exactly. Telegraph lines were essential for connecting people across continents. They really revolutionized long-distance communication, paved the way for the telephone, and eventually the internet.
It's amazing how far we've come from those humble beginnings. Now, shifting gears back to wireless communication, you mentioned that different frequency bands are used for different applications.
Right.
Can you give us some examples?
Sure. Radio waves, with their longer wavelengths, are well suited for broadcasting signals over long distances. That's why they're used for AM and FM radio and shortwave radio, which can reach across continents.
And what about those ham radio enthusiasts who can, talk to people around the world?
They're using those shortwave radio bands, taking advantage of their ability to bounce off the ionosphere.
Fascinating.
Yeah.
So what about microwaves? I know they're used for heating food, but what role do they play in communication?
Microwaves have shorter wavelengths, so they're good for directional communication. They're used in satellite communication, where focused beams are transmitted between Earth stations and satellites.
So that's how those satellite TV signals reach our homes from space.
Exactly. And microwaves are also used in cellular networks, where base stations communicate with their phones.
So microwaves are all around us, carrying data through the air. What about infrared? I know it's used in remote controls, but does it have other applications in communication?
Yeah, infrared communication is typically used for short-range line-of-sight stuff, like remote controls, data transfer between devices, some wireless headphones.
So it's like an invisible beam of light carrying data between devices.
That's a good way to think about it. Infrared signals are pretty secure because they don't go through walls, so their range is limited, but that also enhances privacy.
Interesting. Each type of transmission media has its own strengths and weaknesses.
It does.
Making it suitable for different applications. Now, let's talk about some of the challenges of transmitting data wirelessly. We've touched on interference, but are there other factors that can mess with those wireless signals?
Absolutely. Wireless signals are affected by all sorts of environmental factors.
Like what?
Well, think about physical obstacles. Buildings, trees, mountains, those can block or weaken signals.
Okay. Right.
Weather conditions too. Rain, fog, snow, all of that can absorb or scatter radio waves.
So it's like trying to navigate a maze with invisible walls and unpredictable weather.
That's a good way to put it. Engineers have to consider all these factors to ensure reliable wireless communication.
It sounds like a complex, constantly evolving field.
It is.
Now let's talk about cellular networks. Can you give us a brief overview of how they work?
Okay. Cellular networks are designed to provide wireless coverage over wide areas by dividing the region into smaller cells. Each cell is served by a base station.
So it's like a honeycomb structure,
Right.
with each cell representing a small coverage area.
Exactly. Mobile phones within a cell talk to the base station using radio waves. As you move from one cell to another, the network seamlessly hands over the connection to the new base station.
That handoff always seemed like magic to me. How does it work so smoothly?
Well, it involves some complex algorithms and protocols to make sure the transition is seamless.
And we've seen a huge evolution in cellular tech, haven't we? From those, bulky analog phones to today's smartphones and 4G and now 5G.
We have. The demand for faster speeds and more capacity has been driving that evolution. 5G promises much faster download and upload speeds, lower latency, and the ability to connect tons of devices simultaneously.
It's pretty exciting to think about the possibilities. Self-driving cars, smart cities, the Internet of Things. But before we get too far ahead of ourselves, let's go back to basics for a moment.
Okay.
Can you explain the difference between analog and digital signals?
Sure. Analog signals are continuous waves that vary in amplitude and frequency, kind of like the waves you see in the ocean, like the sound of a voice or the changing voltage of an electrical current.
So it's a continuous flow of information, like a river.
Exactly. Digital signals, on the other hand, are discrete pulses that represent data in binary form, a series of zeros and ones. It's like a series of on-off switches, with each switch representing a bit of information.
So analog is smooth and continuous, while digital is choppy and discrete.
That's a good way to think about it. Digital signals have some advantages. They're less susceptible to noise and interference, and they can be easily processed and stored by computers.
Makes sense. So how do we convert those analog signals, like our voice, into digital signals, to transmit them over a network?
That's where digitization comes in. We sample the analog signal at regular intervals and convert those samples into digital values, zeros and ones.
So it's like taking snapshots of that analog wave at specific moments.
Right.
And then representing those snapshots as digital data.
That's a great way to visualize it. And the more often we sample, the more accurately we can represent it in digital form.
So a higher sampling rate means a better quality digital representation.
Exactly. And once it's digitized, we can transmit it over a digital network with much higher fidelity and efficiency.
It's amazing how we can transform those, smooth, continuous signals into the digital world, the bits and bytes that power our connected lives.
It's a pretty fundamental concept in modern communication, and we can also reverse the process. Digital signals can be converted back to analog to play on speakers and headphones.
So that's how we listen to digital music on our analog sound system.
Exactly. The interplay between analog and digital is pretty fascinating.
I think we've covered an impressive amount of ground here. We've gotten into details of bandwidth, signal attenuation, interference, looked at security measures like encryption, authentication, and even touched on the evolution of cellular networks. It's been a lot.
It has. We've gone from those early analog phones to the super fast 5G networks of today.
It's been quite a journey, exploring how we get data from one place to another, both physically and wirelessly. We've seen the challenges of ensuring reliable and secure transmission, and we've even talked about the interplay of analog and digital signals. But there's still more to discover.
There is. We're going to take a short break, and then we'll be back to wrap up our deep dive into the ever-evolving world of transmission media. Stay tuned.
Welcome back to the deep dive. We've spent the last 2 parts of this episode exploring the wild world of transmission media.
From telegraph lines to the invisible waves carrying our data through the air, it's been quite a journey.
It really has. We've covered a lot of ground, but there's always more to explore, especially when it comes to the future of how we connect and communicate.
Right.
So let's shift gears and look ahead. What emerging technologies are out there that could really change the game for transmission media?
Well, one exciting development is free space optical communication, which uses lasers to transmit data through the air.
Wait, lasers? Like something straight out of a sci-fi movie?
Yeah, exactly. But instead of zapping spaceships, these lasers are carrying data, and they're super fast. Free space optics offers incredible bandwidth.
Wow.
And very secure communication because those laser beams are highly directional, hard to intercept.
So it's like having a virtual fiber optic cable, but running through the air.
That's a good way to put it.
What are some of the potential uses for this technology?
Well, it's being looked at for high-speed internet backhaul, which connects fiber optic networks to local hubs. Also, data center connectivity, and even communication between satellites. Imagine beaming huge amounts of data between buildings or across continents at the speed of light.
That's mind-blowing. It sounds like the future of data transmission is literally going to be very bright. What else is out there in the world of cutting-edge transmission tech?
Another interesting area is visible light communication, or VLC. It uses LEDs, those energy-efficient light sources, to transmit data.
LEDs, the things that light up our homes. How can they carry data?
It's all about modulating the light, switching the LEDs on and off very quickly to encode data. A receiver detects those changes in light intensity and decodes the information, kind of like Morse code, but with light instead of sound.
So our office lighting could potentially double as a wireless network.
Potentially, yes.
That's wild. What are some of the advantages of VLC?
Well, it has the potential for very high bandwidth. It's very energy efficient because we're already using LEDs for lighting, and it's pretty secure because light doesn't travel through walls.
It sounds like we're on the verge of a world where data is streaming down from the ceiling. Are there any other futuristic transmission technologies you're excited about?
Well, one area that's still very early but has huge potential is quantum communication.
Okay, now that sounds like something out of Star Trek. Can you explain it in a way that we can all understand?
Sure. Quantum communication uses the principles of quantum mechanics, this strange world of subatomic particles. It's a completely different way of transmitting data. It's based on entanglement, where two particles are linked, so they share the same fate no matter how far apart they are.
So if you change one particle, the other one changes instantly, even if they're like light years away.
Exactly. And this spooky action at a distance can be used to create super secure communication channels. Any attempt to eavesdrop would disrupt the entanglement, and that would alert the sender and receiver.
That's incredible. It sounds like quantum communication could really revolutionize data security.
It could.
But with all these amazing advancements in transmission technology, are there any potential downsides or challenges we should be thinking about?
Well, like with any new tech, there are always trade-offs. As we go for faster speeds and more capacity, we need to think about energy consumption.
Right.
Wireless signals need power to transmit, and as we have more and more devices and networks, that could mean a big increase in energy demand.
That's a good point. Are there any other potential issues that we need to be aware of as these technologies continue to evolve?
Another thing to consider is electromagnetic interference. As the airwaves get more crowded with signals, managing that interference and making sure communication stays reliable becomes more and more challenging.
It's like that noisy party analogy again. Too many people talking at once makes it hard to hear.
Exactly. It's not just about speed and capacity. It's about finding ways to share the electromagnetic spectrum effectively.
Right. So we need to learn to coexist peacefully in the electromagnetic world.
We do. And we also need to be mindful of the potential health effects of, prolonged exposure to certain types of electromagnetic radiation, especially at higher frequencies. More research is needed, but it's important to be aware of these concerns and use technology responsibly.
Absolutely. I think that's a crucial point. We should always strive to balance technological progress with, human health and environmental sustainability. Well, I think we've really covered an incredible amount of information in this deep dive into transmission media.
We have. From the basic principles to the latest cutting-edge technologies, it's been a fascinating journey.
We've explored the different ways data travels, from those early telegraph lines to the modern marvels of fiber optics and the incredible world of wireless communication. And we've even peeked into the future, imagining a world where lasers, LEDs, and even quantum mechanics could revolutionize how we connect.
It's amazing to think about how far we've come and where we might be headed.
It really is. A huge thank you to you for joining us on this exploration of transmission media. We hope you've gained a deeper understanding of this essential technology.
It's been a pleasure.
And to all our listeners, thank you for tuning in to The Deep Dive.
Mm-hmm.
Keep exploring, keep learning, and we'll see you next time.